Okay, so this is kind of an introduction to like some stuff that we're going to see over and over and over and over again. It's a clear distinction, and we need to make this distinction in order for things to make sense in later units, right? Including this one as well, right? But one of the clear distinctions that we need to make right off the top is the difference between what we call a scalar and a vector, okay? And the 4U's know this, but just to put it down into writing, a scalar is a quantity that is only described by its numerical value, right? And so we call that its magnitude, how big it is, right? But it doesn't tell us anything about the direction in which it's acting, okay? It's just a number, right? And so a vector includes both, right? It tells us how big the force that's being applied is and where it's being applied to, okay? And that can include northeast, southwest. It can be included in a negative or a positive. It's going to indicate on the actual number or afterwards in terms of northeast, southwest, in terms of how big it is and where it's pointing, okay? And so a couple, just to contextualize that, like a few of the like scalar quantities that we know to exist would be distance, and its variable would look like just d, right? And its base unit will be in meters. Okay, and just m. And then mass is also a scalar quantity, right? Can be denoted with a little m or a capital M, and its base unit is going to be kilograms. Okay, and then speed. You'll see why speed, some might say, oh, why is it an S? You'll see why we denote it as a V after. It's a velocity is the vector version of speed, right? Its base unit is meters per second, okay, or m/s. Okay, time is just a little t. It's typically measured in seconds, right? And you guys would have seen some of this stuff in like grade 10 math, 11 math, right? Things like that. I'd imagine most of you take the 3U, have taken the 3U math by now, right? Volume would be a capital V, right? Its base unit would be liters or L. Temperature would be a capital T, and it's be degrees Celsius or degrees C. And then energy is measured as a E, and its base unit is the joule, which we will do lots of work with after. Because I don't expect this to mean much to some of you, right? I suppose the overarching theme here is that if you look at these things, distance, mass, speed, time, like the common theme here is that you can't necessarily, like, you can, but then it turns into something else. You can't put a direction on all of these things. For instance, time, and you put a direction on time, right? So time has no choice. It has to be a scalar quantity, right? Something like distance or speed, they could have a direction attached to them, right? And we're going to see that down here. So distance is the scalar quantity of what we call displacement. Okay, and displacement, this is how we denote vectors relative to, you'll see, I'm just going to write a D here, right? And then you're going to ask yourself, well, what's the difference between this and this, right? Which is a valid question. There has to be a difference because we're talking about two different things. The way we denote vectors, so magnitude and direction, is by putting an arrow over top. Okay, and then this is why we choose the the variable v for speed. It's because speed is the scalar quantity of velocity. So v with an arrow over top. We'll make that look like a v and an arrow. Okay? Whenever we're talking about any vector, we have to think about the magnitude and the direction. Okay? I'm not seeing any questions so far. Are we okay? Okay? So, let's just suppose for a second. We're going to do more like physicsy kind of question in a sec. But what I'm going to try and do with this question is to clearly distinguish distance versus displacement. Okay, so suppose you were to walk from your desk to the pencil sharpener. Okay, it's a distance of 10 steps. What was your displacement? Okay, well, from your desk, relative to your desk, you walk 10 steps. Okay, but then you walked back to your seat. Okay, so you went 10 steps, and then you came back again and you sat down. Well, your displacement. So remember, displacement is like a measurement of where you started relative to where you finished. Well, you finished and started in the same spot, so your displacement is 0. That's the key distinction, right? Displacement always takes into consideration your initial and where you were initial and final. Whereas your distance, what was the total distance traveled? Well, of course, you walked 10 steps to the pencil sharpener, and then you walked 10 back. Well, that's 20 steps. Okay, so that's the distinction that we're trying to make here between displacement and distance, right? And some of that comes out of the fact that, like, let's say the pencil sharpener was over here at X, and you were sitting here in your seat. Well, you would have walked positive 10 steps. And then to turn back around, well, you went in the opposite direction. So that has to be minus 10 steps. Okay, and so when you add these two together, they net out to be 0. That's where that comes from. We're going to see that more in some of these later examples. Okay, so figure 4 here is just kind of depicting the differences between what you would see, right? Like, so for A, this is just a line segment. And then for B and C, like, these are actual vectors, right? This is a vector, and this is a vector. It's a vector because it has an arrow on it, right? It's indicating direction. I don't know if this one is going this direction or that one, right? That's why we can't, it's a kind of just a scalar. Okay. This picture here does a pretty good job as well, kind of depicting the difference between displacement and distance, right? You can kind of see a bicycle going through a kind of a mazy kind of path. That's the distance. But ultimately, from here to here is their displacement relative to where they started and where they are at the end. Okay. So we're just going to run through a couple examples here. Nothing too crazy. Okay. So I wrote above 2. I'll write it again. We can calculate by going delta D, right? You guys should have seen somewhere in your path mathematically. Whenever you're finding the difference between like kind of a final or initial, right, we would have called this delta D. Delta stands for difference. Okay, and that's where this is coming from here. It's a change in displacement, right? Or displacement is the change in D final minus D initial. Okay. So let's suppose we were going to walk from home to school, right? So here's home here. Now the other thing that you're going to see, and we're going to go to school, sir. Get a little bit ahead of myself. The other thing we're going to see here, as we get more and more into the physics, right? It's critical from the standpoint of like vectors that we have directions, like we have some form of reference frame, right? In terms of like a Cartesian grid, right? So typically on a Cartesian grid, and by Cartesian I mean X and Y, positives typically go out to the right, right? And up. In the other directions, we're going to get negative over here, and we're going to get negative down here. So when I look at, or anybody looks at, northeast, south, and west, if I look at a compass, right, my initial thought is to relate these two things by saying, okay, well, east is going to be positive, north is going to be positive, south is negative, and west is negative. Okay. And so we just take that and we say, okay, well, east is going to be positive and west is going to be negative. Okay. And so I'm just going to try and find the displacement for each of these scenarios, right? So imagine we're walking from home to school in a straight line. Okay, what's going to be your displacement? Well, delta D, it doesn't really change, is always D final minus D initial. And as we go through this, the next one, I won't be writing the full word. We'll write df di as we go through here, okay? So D final, remember, we're always referenced to 0. We went kind of 500 to the right, right? So that's positive. We went east. East is positive, so I said positive 500, right? And then what's my initial? My initial was 0. Okay, so what's the answer come out to be? Well, it's positive 500. Okay, well, that means, don't forget your units. I'll try not to forget units. 500 meters, right? Positive, in the positive direction. Well, what's in the positive direction? East. So your answer would be 500 meters east. Okay? But what if I decided, okay, well, what is your displacement if you walk from school to the library? Okay, so you're standing at school. All right, we're going to go delta D, D final minus D initial. Okay? I'm going to say, okay, well, what's the final? Well, the library is way over here. It's like 1,200 meters, right? So we're going to say, okay, well, positive 1,200 minus, what's my initial spot? Well, my initial was, I was going from the school, right? So the school is positive 500. So it's minus positive 500. So we basically get 1,200 minus 500, right? And so you're going to get 700 meters east because the answer came up positive. Right? So you know, okay, the displacement is towards the east because the number came out to be positive. Okay? And then we go down one more. One night after working at the library, you decide to go to the mall. What's your total displacement when walking from the library to the mall? Same thing. Displacement is defined as df minus di. Right? Where did you finish? Oh, you finished way over here. 1,000 meters west. Minus, what was your initial spot? Well, 1,200 east. So minus positive 1,200. Right? And so you're going to go, okay, well, negative 1,000. Take away 1,200 more. That sounds like negative 2,200 meters to me. Right? Well, if it's negative, we know that the negative is acting in the west direction. Right? And so we're going to say, okay, well, the displacement is 2,200 meters west. Okay? Anybody have any questions? Send me a message if you want. Okay, if you don't have any questions, we can, I'll jump to the next question. Okay, so a dog is practicing for agility competition, right? So She leaves the trainer and runs 80 meters due west to pick up a ball. Then carries the ball 27 meters due east and drops it into a bucket. Okay, so let's draw the scenario out. Right? We've got to start. And then the dog's going to run 80 meters, right? In what I'm presuming to be the negative direction, right? Because we're running west, right? Right? And then it stops and turns around. And it eventually just drops the ball in the bucket after going 27 meters in the positive direction. So it's final. Okay? So, a little bit trickier from the standpoint of like wrapping your head around this, right? But remember, we started at like 0 meters, right? So this is your DI. And we need to figure out, okay, well, where did the dog finish, right? Well, we ran, like, what's DF? Well, the dog ran negative 80 meters to the, like, in the west direction, and then turned around 27 meters, right? And so your DF value is going to be 53 meters. Okay. Now, sorry, negative 53. Now, the importance of doing it this way, I know most of us could probably go, okay, well, they ran 80 meters to the left, and then 27 meters to the right, right? So we could say, okay, well, we know that the dog finished on the left side of the like the 0, right? So we know it's in the west direction, the total displacement. But what if, the reason why I show you this method here, like figuring out what DI is relative to DF, is because what if we're not starting at 0, right? Like in terms of our reference frame, like maybe we started at 50 meters on the towards the east, right? That's going to change the displacement. The initial value changed, right? The initial displacement value, right? And so your total displacement is going to change, right? So if you just go, okay, well, we ran 80 meters to the left and then 27, well, that's negative 53. Well, that's on the left side, right? Well, it depends on where your reference frame is, right? And what your starting value was, right? And so just for consistency's sake, I'm still going to write this out. Right? Except we know that, this is kind of a method that will work 100% of the time. It will work 100% of the time because you're taking into consideration the initial value, right? And it's just nice. This question is nice from the standpoint that DI is 0, right? And so your total displacement here is the negative 53 minus 0. Which turns into 53. Okay? That answers the dog's total displacement. How far did the dog actually run? The distance would be, okay, we don't really care about the direction for distance, right? Distance is just how far did the dog run? Well, it ran 80 meters. Doesn't care about that it turned around. It's just distance ran, right? So 80 plus the 27, that's going to equal 107 meters that the dog ran. Okay? That's the distinction. You'll see I didn't put a direction on here, right? Relative to the vector displacement, right? That's the distinction between distance and displacement. You'll see the same distinction between speed and velocity. Okay, we're going to do that now. I'll try to get this done in the next 11 minutes. It's 2 low questions, okay? So the average speed of a moving object is the distance traveled, right? divided by the time. Okay. VAV is the average speed. Delta D is the distance traveled. Okay, so same thing. Okay, and it's divided by the change in time. So for instance, this is just kind of a reference. Like grass, in case you guys haven't heard of grass before, we've got givens, requireds, analysis, solution, and statement. Okay, the statement is being like the therefore statement right at the very end. So what you do, and I just like following this sometimes. Like I don't write out the word grass anymore, but I'm always been in the habit of writing out the things that I know and the thing that I don't know. Right, that's just, you need to do that. Right. So the things that I do know is the distance. Okay, well the D is 43 meters. Right, and T, it told me how long it took. Okay, 28 seconds. Right? What's the thing that I'm looking for? What's your dog's average speed? So BAV. All right. Well, we conveniently know what VAV is equal to, right? VAV is equal to the change in distance over the change in time. I think again here we're just talking about the fact that we're starting at 0 and then it ran 43 meters, right? So the distance value is going to be 43 and divided by 28 should be 1.5 meters per second. Now, how do I know that the units are meters per second for this? Well, this comes into a conversation. This is what physics is nice for in terms of it puts some of the things that we emphasize in math into context, right? If I were to put my units here, you guys know that this means division. Well, if that's division, then your units better be division. Meter divided by second. That's how you can see the speed. 1.5 meters per second, right? And then so your statement, therefore, okay? Now, average velocity is a little bit more complicated from the standpoint that we now need to take into consideration the direction, right? And so the average velocity takes into consideration, it can't be distance, right? Because velocity is a vector. So it has to be very similar to speed in the standpoint that we have like the units have to make sense, right? So we still have to get meters per second for velocity, but it needs to take into consideration this direction piece, right? And well, we just spent a whole bunch of time talking about the relationship between distance and displacement, right? And so the average velocity of an object in motion is its displacement, right? Or change in position divided by the total time. Okay, you'll notice nothing really gets mentioned about time because time's a scalar. We can't just assign a direction to time, right? The velocity describes the change in position over time, okay? And so, for example, a cyclist traveling at 11 meters per second has a velocity of 11 meters per second east, okay? And so what we're going to spend some time doing tomorrow is looking at graphs like this and pulling some math context that you guys are familiar with from grade 9 and 10, which is slope, right? And so a position time graph, I didn't leave much room here, is a graph that describes the motion of an object with displacement, or I suppose, yeah, displacement, because it has direction, and time on the horizontal axis. You'll see that down here, time and displacement. Okay? If you guys look at slope, what is slope? Slope is rise over run. Well, what are you going up by? What is this? What are the units of this axis? Meters. So you're going up it doesn't matter how many meters, you're going up, the units are meters, over, well, time measured in seconds. Right? So you can see the slope of this, rise over run, measures velocity. Right? Gives you the units of meters per second. Right? Or change in displacement over the time. Gives you this. Well, this is average velocity. Okay. Well, one more question, and then I got a couple other things to talk to you guys about before you go. Okay. On a windy day, the position of a balloon changes as it is blown from 82 meters north away from a child in 15 seconds. Okay. What is the average velocity of the balloon? Okay, well, we're given. You just look at the question and look at what you're given. Okay. Well, your change in position, right? So it's displacement. Delta D is equal to 82 meters north, right? And we also know the change in time. What's the thing I'm looking for? Do I leave it VAV? No, because I'm not talking about speed. I'm asked for the average velocity. It's a vector, so we write an arrow over top. That's what I'm looking for. Okay. Well, we know this doesn't change anything. It's just the fact that it has a direction tied to it, right? So we're going to have VAV is equal to the change in displacement divided by the change in time. Right? What are the numbers? Well, you wrote down what the numbers were, right? We're going to have 82 meters divided by 15 seconds. Okay, well, that's 5.5 meters per second. Okay, that's its speed, but it's not the velocity. The velocity has to have the direction. Right? So therefore, okay, I'm going to stop it there. So